is our mainline instrument. This is a selected ion flow tube mass spectrometer, shortened SIFT-MS. Unlike traditional mass specs, like a GCM mass spec, what this basically does is, where the GCMS basically fragments the ion with a 70 electron volt source, this does what's called a soft ionization. So what it does is it takes water vapor or air, and using a microwave plasma source, it effectively ionizes it into positive and negative ions. We have H2O plus, we have NO plus ions, and we have negative ones too. We have like OH minus, O minus. And so there's effectively chemistry going on in this. So what it does is it takes those precursor reagent ions, they go into the sample stream and they'll react with whatever analog or whatever's in there. What you end up with some product ions with very specific mass to charge ratios. What we do is we can look at those product ions because they're now charged either positively or negatively, and we can determine what they are. Now, there are some limitations to this. So unlike a GC mass spec where you have a column that can separate out compounds with a certain degree of resolution, this is looking at everything at once. So there's some things, some analytes we can't differentiate. Like for instance with this, ethylbenzene and xylenes, we don't know. They have the same mass to charge ratio. So we lump them all together. But for other things like benzene, toluene, butadiene, styrene, we're pretty solid. And then also for hydrogen sulfide. So you saw the cavity down spectrometer over there. We can duplicate it with this. It's not the same technology, obviously, but we can look at it, and we've already done comparisons, and it shows you the almost within plus or minus 1 ppb what the concentration is of our spectrometer. So it's an incredibly versatile tool. We can look at thousands of different compounds with this, at least, again, that are uncalibrated methods. Our calibrated methods we currently have are for halogenated compounds, halogenated VOCs, hydrogen sulfide plus BTEX, butadiene, styrene. We can look at uncalibrated methods that we have are for mercaptans, and for potentially in the future we're going to be doing things like amines. We have an ethylene oxide method on this. The only thing is that at very low levels, the interference acetaldehyde is present everywhere in the atmosphere. It's all the time. It's very low concentrations, like anywhere from 6 to 10 parts per billion. However, because it has the same mass to charge ratio as ETO, at very low concentrations, we can't subtract it out. For higher concentrations, above 10 ppb, we can subtract it out and have pretty accurate measurements. So again, everything's not just straightforward. Now, to be very honest with you, this is an incredibly easy instrument to operate, which is essentially you push buttons. There are already pre-programmed methods. To develop the methods, to calibrate the methods, that's a lot of work. It's a lot of hard work. And that's where, the front end, as I said, is where all the work goes in. Once we have it out in the field and the methods are developed and ready to go, you just basically push buttons and you get the data. It gathers data every 2 to 3 seconds. So over an hour period, traditionally we had an old GC, we could get 3 data points every hour. Now we can get thousands.